we actually have a good story to tell now, which started with testing, continued with Erlang, then testing again, then application architecture, or application structures, which is all the talks that Jan has been giving before at the clojureD. By stepping in here, he is now officially the only speaker who spoke at every conference that we have here. That's an extra applause, isn't it? Yeah, every clojureD. Today he will be talking about compiling Clojure somehow to native stuff and running it. And so please welcome, these days from Berlin, Jan Stępień.
Thank you for this warm introduction. Good morning, ladies and gentlemen. It's wonderful to be here with you again in Berlin. My name is Jan Stępień. I'm a consultant at InnoQ. I live here in Berlin, where I work with people to build better software. Enough about me. Let's talk about native Clojure. Before we start, we need to, this always works, we need to talk about some background, specifically about compilation and virtual machines. When we start programming in our favorite JVM-based programming language, Scala, Java, Clojure, Ruby, you name it, we start with this abstract, lovely representation which we people enjoy a lot, code, right? And then we start by some sort of ahead-of-time compilation, where we translate the code we understand into a representation which is understood by machines. We translate it to this JVM bytecode. Resulting class files or classes might be persisted on disk, like we do in case of Java or Scala, or just kept in memory, like in case of a typical Clojure development scenario. And we don't stop here. We move on, and in the next step, we let the just-in-time compiler do the actual heavy lifting. We go from this abstract machine-independent representation of class files and classes into native code optimized for the particular physical machine we are running on. Both of those aspects are interesting. We will spend most of the time with the ahead-of-time compilation today, but allow me to briefly talk about last 20 years in just-in-time compilation and the world of JVM. For past 20 or so years, we've been using Hotspot. Hotspot is a brilliant piece of engineering. It's this virtual machine which has matured, has evolved very well as we change the way we write our Java programs, as we introduce more and more programming languages onto the JVM, which have completely different requirements, benefit from completely different optimizations. Hotspot has been doing a great job making those programs run fast. The problem is it's still a million lines of C++, and this code didn't age well. And at some point, engineers at Oracle decided it's time for a fresh start, beginning again from a green field. And they attacked the problem in two stages. They started by publishing this new compiler interface. Since JDK 9, JDK comes with this interface, allowing you to plug in dynamically your own just-in-time compiler into the virtual machine, allowing you to implement an interface which looks like, given this method, produce the following bytecode. And now you can write your own compilers. And then in the following release, they filled the gap by introducing Graal. Graal is a whole suite for compiling programs which implements this JVM compiler interface. And it acts as a replacement for Hotspot. It allows us to compile JVM bytecode into machine code just in time as the machine is running, producing very efficient code. And funnily enough, the thing is written in Java itself, so when you start JVM, it begins by compiling itself. So when you look at some architectural boxes, we see that we have this good old JVM we know and like, which communicates with this new compiler over the JVM CI protocol. Graal is this new compiler, which still operates at the bytecode level, which is suboptimal for those of us who want to implement their own programming language but don't know specifica of JVM bytecode. So on top of that, they built a couple of extra abstractions, such as the truffle framework, allowing us to express semantics of our programming language using a high-level representation and compile it down to GraalVM using this nice abstract representation. This allows language implementers, for example, folks behind Truffle Ruby, to implement Ruby on top of Truffle, allowing it to run on GraalVM, creating, to the best of my knowledge, the fastest existing implementation of the Ruby programming language. So that's fascinating. The tool supports a whole lot of programming languages, and including, among other things, C and C++ by implementing LLVM bytecode. So it's really impressive, and this is the just-in-time part. Now let's move to another interesting addition, the native compilation. You can get the entire package from graalvm.org, and this native part brings us to the main part of today's story, that is native Clojure. The ability of compile, using Graal toolkit, compile JVM bytecode into native binaries for your favorite operating system, as long as it's Mac, Linux, or I think Windows. We get a copy from GitHub, where we get this solid bundle of 200, 300 megabytes, including implementations of a number of programming languages, showing you how language independent the whole toolkit is. And among many cool things inside, we will find native image, a binary which is translating precompiled JVM bytecode into native, fairly optimized binaries. Let's talk about a simple example. JQ, I hope you know the tool. JQ is this lovely small tool allowing us to read JSON from the standard input and do some nested lookups in our JSON documents. Let's do the same thing in Clojure. I don't need much, right? I need to pretty print something, so I'm requiring the corresponding namespace. I read data from standard input, parsing it, that is, I'm reading Eden data structures, and then I'm performing a nested lookup using this getIn. The path comes from the standard, from command line arguments, and I pretty print the results. Let's go the traditional way. We compiled the thing firstly to JVM classes, then we built an Uber jar, and if we run it traditionally, we get 1.5 seconds of runtime, and we need at least 100 megabytes to finish the task. JVM is a very flexible environment. So by adding one more flag, we can change runtime characteristics. By instructing the JVM, don't spend too much time compiling, this program won't be running for that long, so hold with the just-in-time compilation. Now we can save a bit of time and also save a bit of RAM because we don't need to keep so much information about the runtime characteristics of the program in memory. So that's the story on the JVM. Now there's another option. Lumo is a brilliant piece of engineering, right? It's this very clever combination of existing tooling and all the work which went into Node in order to speed up startup of ClojureScript. So if we now rewrite our example in ClojureScript, we halve the time of execution, and the memory usage is similar because we are still running a similarly complex virtual machine optimizing the whole code. And now the main part. We run native image, the thing which comes from the GraalVM package. It takes solid 2 minutes and all the RAM it can find on our machine, and we end up with a drastically different situation, right? It's just surreal. The startup time disappears, and the memory usage is also essentially gone. Let's take a look at numbers, right? It's incredible. We will return to the question of how is any of that even remotely possible, but firstly, let's think about potential applications of this new development. Let's talk about command line utilities. I'm very close to the Unix philosophy is close to my heart. Small programs doing one thing, doing it well, operating on simple data structure that is text. Let's see how this new development allows us to implement Clojure-specific command line utilities. For example, something translating JSON to Eden. We will repeatedly read stuff from the input, specifically JSON documents. We will keep reading them until we hit the end of file. If we never get to the end of file, infinite streams are fine as well. We keep reading until the end of file and finally print all of the resulting data structures. If we compile it and run native image on it, we can use the tool to parse simple package.json files coming with every single node package, and the runtime characteristics of a Clojure program are completely different compared to what would happen in a normal JVM environment. Okay, now we can translate arbitrary data into data native to the Clojure environment. What can we do with those? Not long ago, I ran into this very interesting project called Spec Provider by Statistidaris. What Spec Provider is, it borrows ideas from the world of F# and type providers. It looks at several examples of a data structure, and it tries to figure out this spec, the Clojure spec, which spans all of those examples. Let me show you an example which I stole from the README file. If we have 3 maps, and we call infer specs, we have this inferred specification spanning all of those data structures. We can then pretty print them and indeed learn that the small map is something with keys A, B, C, where A is an integer, B is a string, and C is either a keyword or a string. Now we can use it to build some tool around it. Same structure, right? We've seen this before. We keep reading stuff from the standard input. This time we have to read till the end. It doesn't work on infinite sequences. And then we call print specs to print the resulting specification. Before we run it, let's add one more tool to this pipeline, specifically zprint. Zprint is one of the pretty printers for Clojure, allowing us to stream the spec we have deduced and pretty print it so that it's ready to copy and paste it into our source file. Luckily, we don't have to do anything in this case because, as you can see in this slide, zprint comes with native image precompiled binaries for a selection of operating systems. So the resulting pipeline looks like this. We take a handful of package.json files I found on my disk. We translate them to JSON, to Eden. We run spec provider on them, and finally pretty print them, resulting in a Clojure spec description of package.json files within, well, less than a second, taking 100 megabytes of RAM. Instead of starting 3 independent JVMs and waiting a tad longer. Which I find fascinating, right? Because this opens a new avenue for Clojure-specific command line utilities. Back. Let's talk about web applications, which is another thing which is dear to my heart and represents another interesting, represents an increase in complexity compared to nice toy tools we've been playing around before. But this is my user story. This is all I want to have. I have a key value database, and I can put key CT value Berlin, and then I can get it back. It would be lovely if this web application also persisted data as flat files in the temp directory. To implement this entire API, we need like 70 lines of Clojure. I don't want you to read that. That's way too much code and too small font. All I want to say is that we need that much, 50, 70 lines of code, to combine a couple of tools, such as BD, some Ring middlewares, and HTTP kit, and have a normal, ordinary Ring web application, which after being compiled is around 7 megabytes in size. I'm talking about the actual uberjar with all the components. And then we can precompile this application using native image, resulting in a small binary, self-contained binary, including both the HTTP server and all the things serving this entire user story to the user. Okay, lovely. And now instead of talking about runtime characteristics, let's talk about something else. Let's talk about the operation story, the deployment aspect of the whole thing. And let's package this piece as a Docker container. We will start from Ubuntu as our base, and we will install all necessary dependencies. So stuff which is necessary to run native image and stuff necessary to compile Clojure. We will copy project CLJ, run Leiningen1 to cache all the dependencies neatly, then we will copy all of our relevant source code, run Leiningen again to build an uberjar, and finally build this single self-contained binary. And now the twist comes. We start from scratch again. We start from a completely empty Docker image with not a single file on it, and we just copy web key value main onto the root of our new file system. And that's it. We're done. The resulting Docker file has 13 megabytes in size and consists just of a single file, fulfilling all of the requirements of our web application. And what I find most interesting is all the stuff which is not there. All the parts of the operating system, virtual machine, probably Vim, and other things which would be in your normal Docker container but are not there, and you don't have to worry about them, about the problems they might cause, about security vulnerabilities which might be there. You have just one thing, right? I like having fewer things to think of in my head. So that's fascinating, right? We have self-contained, small applications, easy to deploy, wieldy, and having all the dependencies, all the necessary stuff built into them. And at this point, we can move on to the important question, is how is any of that even remotely possible? Let's take a look at the numbers again. Numbers, yes. The right column, the memory usage, is a bit easier to explain. When you think about it, both JVM and Lumo, that is V8, have this entire just-in-time compilation machinery in them, the entire virtual machine responsible for keeping track of all the method executions, then generating corresponding code for methods which are hot, de-optimizing them, optimizing them again, inlining them. This takes a lot of space. So this explains the difference in memory. Since the natively compiled image has next to nothing. The virtual machine embedded in those binaries is called substrate VM, and it consists just of a garbage collector. And that's roughly it. You don't have anything but the garbage collector inside. So we can sort of explain what's the difference in the memory column. The time one is far more interesting, and this difference is especially pronounced in case of Clojure applications. And to understand this difference, we have to go a bit back in time and look at some interesting historical blog posts. And this piece from 2014, Nikos Kalerimi describes results of compiling Clojure code into bytecode, then decompiling this bytecode into JVM sources, and looking at resulting JVM. What is the Clojure compiler producing, and where does the startup time go when we compile Clojure and then start it from those JVM classes? And it's very interesting. Nicholas discovers that a lot of the cost, a lot of heavy lifting happening when we start Clojure applications happens in so-called static class initializers. Static class initializers are part of a normal part of Java classes. You can have this piece of Java class, a bit of code, which is executed the moment you load your application into the memory, when the class loader reads your class. And Clojure is doing a whole lot of work in those static class loaders. For example, It loads and it instantiates namespaces. It creates vars, assigns vars to namespaces. It instantiates functions and metadata, and assigns those to metadata. It recreates the entire universe of our Clojure environment, namespaces and all this stuff, filling them. And all this stuff is happening, most of this stuff is happening in static class initializers. And the reason why we see such a massive difference in startup time in case of native image is the fact that native image runs this code at compile time. All of this code to recreate our namespaces is run when we compile our native binaries, and the resulting state of the application is just persisted into the binary. So when we start the application, it's just there. It's just there, and there's nothing left to do apart from open connections to your favorite databases. In another blog post from September last year, one of the engineers working on GraalVM describes in depth this process, how initialization of classes works, how we can control this behavior. For example, if we want certain parts not to be initialized ahead of time because we need to initialize something at runtime, GraalVM gives you tooling to control this behavior. All right. There are some limitations. There are some limitations we have to be aware of. And the team behind GraalVM maintains this nice list describing all the problems which might happen, which some of them are more, some of them are less relevant to Clojure. Let's take a look at two examples. One of them is reflection. Reflexive calls, that is when we actually take a string of the name of the method or a name of a class and ask the JVM to figure out the actual object for us. They are difficult when there is no virtual machine in the resulting binary. There is nothing to answer the question. So theoretically, this could be a big problem, especially well, on one hand, on big frameworks relying on dependency injection and figuring out names of classes at runtime. In Clojure, that's not much of a problem, as it turns out, because we have tooling to remove reflections and reflective calls. Using warn-of reflection, we can ask the compiler to inform us, hey, this is a reflective call, you will have either performance problems or native image will not be able to compile this code efficiently or at all. So that's not much of a problem, but something to keep in mind. And the second thing I'd like to bring up is dynamic class loading. Something which on the JVM is, well, our daily work, especially in the REPL where we keep recompiling the code and loading new classes, unloading old ones and having them garbage collected. However, in Substrate VM, there is no virtual machine to load classes into. As a result, everything touching class loader is not allowed on Substrate VM, won't compile using native image. As a result, Clojure core eval is out. Same for functions using it, like require and so on. All of them load new classes. So this is a problem in our day-to-day development work, where we keep interacting with a single environment, and we don't work with the machine, but in the virtual machine. However, in production environments, we typically have everything compiled ahead of time, right, into those static Uber jars. So once again, it's something to be kept in mind, but not something which affects us that much, allowing us to use this GraalVM native compilation technology to its fullest. Okay. We've talked about quite a lot of things today. We started with those just-in-time compiled programs written in Java, which can be highly optimized on Hotspot. Hotspot being a virtual machine, being a fascinating piece of technology which scaled very well with our changing ways of programming Java applications. Hotspot has scaled very, very well. But at some point, there was a time to introduce a new technology stack, a new compiler stack. And as a side effect of this stack, we got this not only very efficient, very fast just-in-time compiler, but also the ability to compile native code, compile JVM bytecode into native code, which opens a lot of potential avenues in case of Clojure. New places where you can employ Clojure, where previously we were limited by high memory usage or by startup time. Those problems are addressed by this technology. So I encourage you to download it, give it a go, give it a spin, see how it works, see it break, and understand why it broke. Go to your local meetup, give a talk, write a blog post, share this information so that we can learn together how to understand this tool and explore new areas to use Clojure in. My name is Jan Stępień. You've been a wonderful audience. Thank you all very much.
So we have time for questions. I think it was first
one. Are native images always faster and smaller than JVM bytecode plus just-in-time compilation?
They are surely smaller. They are smaller because they don't package the entire JVM with them, so you're saving the size of the entire JVM. The smallest JVM, just to give you an example, the smallest JVM I was able to find on the Docker Hub was 70 megabytes, and the resulting binary was 14 megabytes. So that's the order of magnitude I saved there. And when it comes to speed, well, that's interesting, because you save a lot of time at the startup time, but then the top speed, especially in CPU-bound tasks, is higher on the JVM. If you have the entire just-in-time compiler, then after some time, JIT will do the work well and result in way faster code. Simple examples, which I compared using JVM 8 and the community edition of GraalVM from half a year ago, show that just-in-time compilation, the normal JVM, was twice as fast at the end of the day after a couple of minutes. I hope this answers your question.
Hello. I want to make sure I understood something correctly. You had this slide where you showed the Docker setup, where you compiled it and then you started from scratch. The resulting web key value.main, this is an executable? This is something that you can execute directly from the shell or something? Or what is it? The
yes. This is a normal statically linked Linux executable, a normal AMD 64 native executable. You can have it both statically linked with everything built in, or shared, or a version depending on all the shared libraries like libc and what have you. But it's a normal executable.
Hello, thanks a lot for the great talk. What about all the options we have for the runtime behavior, like garbage collector options? Are they also available with the GraalVM?
I'm sorry, I didn't understand acoustically.
What about all the options we have for the runtime, let's say garbage collector options? Are those available as well?
I'm afraid they are not. I think you have far less control over the runtime behavior of those binaries, especially since they are, well, they don't have the virtual machine which would respond to those options. I guess you can control the size of the heap you give to the garbage collector. And as for the rest, I would have to ask you to read the documentation of the tool.
Hi, great talk, thank you. What is the story for playing together between Graal and WebAssembly? Because WebAssembly is kind of in the same unifying space.
Speculation follows. WebAssembly, correct me if I'm wrong, can be compiled to LLVM bytecode. Yes. And if it can, GraalVM comes with a truffle-based implementation of LLVM. So it can execute LLVM on top of truffle that is on top of GraalVM. And GraalVM at this point doesn't care about languages anymore. For its internal purposes, everything's the same. As a result, you can have a single Java, Clojure, Scala, you name it application, calling WebAssembly stuff, and GraalVM just doesn't care anymore. From its perspective, this is Graal and this is Graal. So Optimizer inlines one into another, inlines your WebAssembly into your Java methods. This is how the Ruby implementation is so fast. Because the Ruby implementation, for example, when it comes to C extensions, it compiles C extensions through LLVM and then to GraalVM internal representation. And then Ruby calling those C extensions results in inlining C code into Ruby methods. It's fascinating.
Yep, thanks. Cool.
And thank you for the call. What's the current status of the ARM CPU support?
I do not know.
ARM
I'm sorry. The ARM situation is unknown to me. I know it works on, like, the 64 standard AMD 64 platform, and I see how ARM would be very, very interesting as a platform for those tiny binaries. You'd have to take a look at the sources. Sorry, I don't know.
Hi. Thank you very much for the call, for the talk. Already made my day. I have a joint question. It's about the production readiness boundary. I call it boundary because are there kind of application you would not use GraalVM if it's, for example, for a mission critical application for a large customer? And the connected question is, there is a lot of data mining software in Python. Would you consider, if you are interested in large software packages in Python, consider using GraalVM to work in Clojure and calling those libraries?
Well, thank you for your warm words. And that's a very good question when it comes to what would I do in mission critical situation. On one hand, the GraalVM acting as a JVM has been tested in production by folks at Twitter for some time now, and their story was very encouraging. They had some Scala services running in the backend, in the underbelly of Twitter, and they were very happy with the performance. And this was a couple of releases before. But this is still talking about the normal JVM with Graal compiler. Native code is, we're still at release candidate before 1.0. So if it's something which, so to speak, matters and can lose a lot of money, I cannot recommend it. And in the current state, experiment and play around. When it comes to the second part of the question about Python machine learning and the story with Clojure, yes, why not? GraalVM, thanks to its language agnostic characteristics, should be able to allow you to import parts of the Python code, compile them, or just run your Python code in the same environment as you run your Maria.cloud environment, and then have one embedded into another and very efficiently executed on the same platform. But again, I'm so deep into the realm of speculation right now.
Still very interesting. Thank you.
Okay, last question.
I would know, how is this error tracing then going on? Is there, if you run this natively, what kind of stack trace you get?
Are you talking about the native thing or the GraalVM?
The native.
The native thing.
Is it like when you produce an error, or you...
They were, so to speak, as readable as normal Clojure stack traces. As in, they were the same. The stack trace was, so to speak, preserved probably at points where methods were thrown. Whenever GraalVM saw that there is a throw bytecode, it embedded the entire stack trace. So I guess it's okay.
So a pun on Clojure stack traces, that's a very nice ending of a talk. Thank you very much.
Thank you so much.